Here's the time in case of any uploading issues. Okay. So, number 6, part A, wants us to find the speed of the object after it has fallen 80 centimeters. So, we have to find, or we have to at least get variables for our tensions first, because that's going to help us find our speed. So I have this one as TR, tension right, and this one TL, tension left, little m, big M, and I think that's all. Okay, so what we're gonna set, so this is also, we're gonna call this object, and then this is sphere. Okay. So first let's set up force for our object. And that's gonna be FG of object. And that's, so we have it FG minus TR because your FG and your TR are both acting on the box, but your FG is what is bigger, so big minus small. And then you can go ahead and expand this and rearrange it. Okay, so that is our first tension. We also need to find the second one. And for this one, we're going to set up torque of sphere, and that's going to be equal to your FTR equals I sphere alpha sphere. Okay. And then we can go ahead and put, so on the sphere, the only perpendicular force is your TL. So you can go ahead and put TL R is equal to, it gives you your, well you have, it's a sphere, so it's 2/3 big M R squared. And then you can go ahead and convert this to, you can get A over R because of that. Okay. And then you can go ahead and cancel out your R's, so you get TL is equal to 2/3 MA. Alright, now with this, we can go ahead and set up torque for the pulley. That way we can find acceleration. That way it'll help us find V. So you set up torque for the pulley, F perpendicular, R which is equal to I pulley times alpha pulley. And then this is going to be equal to TR minus TL times R, which is equal to I pulley and alpha pulley. Okay, now from there we have TL we can plug in, and TR we can plug in, and that gets you mg, this mg minus ma minus 2/3 big M A times R is equal to, and then the rest, I pulley, alpha pulley. Okay, and so now we can distribute the R. So mgr minus mar is 2/3 big MAR, which is equal to IP. We can convert that again to A over R. Okay. Now what we can do is move this and this over because they all have A. So you can go ahead and put I pulley A over R. I pulley A over R plus little MAR minus, or plus, sorry, 2/3 big MAR. And then from there, you can pull out A. So you get A, and then I pulley over R plus MR. It's 2/3 big MR. Alright, so we want to solve for A, that way we can find V. So we would just divide all this over here. So then you get A equals MGR over I pulley over R plus MR plus 2/3 big MR. And then you can go ahead and plug in all your numbers. So the mass of the small object is 0.5. Gravity is 9.8. And then the radius is going to be 5 centimeters, which converts to 0.05 meters. And then it's all over. So I believe they give you I. Yeah, they give you I. So that's 0.003, and then your radius of 0.05 plus, and then mass again, little m, 0.5, your radius is 0.05, and then your plus 2/3. Your big M is 5, and then again your radius 0.05. Okay, and now you can go ahead and just plug this all in your calculator. 0.0. You get 0.98 and then meters per second squared. Okay, so then you can go ahead and you can use your common form. So delta y f squared minus vi squared over 2a. Alright, and this is your acceleration, and it tells you that it dropped 80 centimeters. So you can go ahead and plug all that in. So 0.8, which is equal to, so you have no VI, so that's 0. And you're looking for VF over 2, and then your A is 0.98. VF squared is equal to 1.568 square root get 1.25. And then this is meters per second. Okay, so that is part A. Okay, so now part B. Find the time it takes to fall to 80 centimeters. So you can just go ahead and set up your distance formula. VRT plus 1/2 AT squared. And again, you have no VI, so you can just plug in everything, 1/2, and then you can use that acceleration again. And then T squared. So this is and then you get T equals 1.28 seconds. Okay, now C, determine the shell's rotational kinetic energy after the 80 centimeters. Okay, so you can go ahead and set up KE rot for the sphere. And then KE rotational is 1/2 I of the sphere omega sphere squared. And then that's going to equal 1/2 2/3 big M R squared. And then omega sphere squared. Okay. So we need to find omega. So we know that V equals R omega, and so that means omega would equal V over R. And we found our V to be 1.25, so we can use that. 1.25 over RR. So the R for the sphere, or the shell, is 10 centimeters. So that would be 0.1 meters. Just plug that in your calculator. 12.5 rods per second. Okay. So you can use that for your omega. So then now we can just plug everything in. So you get 1/2, 2/3, and the mass is 5. And then again, your I is 0.1 squared, and then 12.5 squared. And then again, plug that all in your calculator. So 0.1. And that gets you 2.5, we can round that up to 8 joules. And that is your KE rotational of the sphere. Okay, so I don't think I'm going to have enough room for D. So D wants, what is the fraction of total energy that has been transferred to the pulley? Okay. So, alright, so first we can find total energy. So it's going to be equal to your PEI of the object, because if you think about it, this has a falling height, so it's the only, and since these don't have a height and aren't moving, this is the only thing that has energy at rest, or has stored energy at rest. So it can be PEI of the object, and so then that's just equal to mgh of the object. Okay, and then we can go ahead and plug everything in. Mass 0.5, gravity 9.8, and the height was 0.8. And then we just plug that in. That gets you 3.92, and that is joules. Okay, so that is our total energy. Now we need to find how much energy in the pulley. So the pulley is going to have a rotational KE. So we have KE rot pulley, and then 1/2 I of the pulley and squared. Okay, and then so again we need to find omega. We have V over R, and again we can use this V, so 1.25, and then the radius of the pulley is 5 centimeters, so that's going to be over 0.05, and then plug that in. Gets you 25 rads per second. Okay, so using that, you can plug that back into this, and it gave you I of the pulley, so 1/2 0.003, and then our 25 squared, and then calculator. Okay, that got 0.9375. Okay, now that we have joules, now that we have both of those, we can find the fraction of the total energy that has been transferred to the pulley. So we can put the kinetic energy of the pulley over total mechanical energy. So that gets you 0.9375 over 3.92. And then you can go ahead and reduce that. And that gets you 0.22392 over 1. And then joules. And that is the fraction of how much energy was transferred to the pulley out of the total energy. Make sure to box everything. And that is it.